Hello everyone, this is Ricardo Lu. Welcome to Lab 3, Task Classification. This lab is prepared by Yifan, Ricardo Lu, and Professor Yilu Zhou. This time, I'm going to complete a task of detecting scams. This lab will introduce 4 classifiers and 3 approaches to construct features. By constructing features, I mean that we get text object as input and we construct features that only contain numbers. Right now we have 4 classifiers: naive Bayes, decision tree, random forest, and neural network. Neural network is optional that you need to learn. Also, we have 3 approaches to construct features. The most important ones are backwards and TF-IDF. It is optional for you to learn and know where to back. This is a neural network way of generating a feature. Thus, we have 12 results to compare in our final table. By the way, let me clear output and I will start running the program. Let's start from the beginning. We import packages. I have a reminder that if you have problem, import some of the packages. Don't be panic. Just search the ones that is missing. Things like Jennison. You just need to pip install Jennison. When it fails, for some reason it cannot run, Google it. You'll find out your result. Let's continue. We load the data. The most important thing when you start doing a program is look at your data. Right? You have category, you have message. The categories are ones and zeros. And you have messages like, I want to look at the first message. It looks like a scam or something. So I look at it. I want the first one. Interest rate at the lowest at 40 years. We help you find the best rate for your situation, matching your needs to hundreds of lenders. So it's a scam. That's why it's giving you 1 as a result. So 1 means scam. That's a cue for me. So for me, I'm interested in the last one. Okay, I cannot get the last one for some reason. How about 4,000? Haven't heard anything about this. So excuse me, Pod, but blah blah blah. Should back some report somewhere other than it sounds like a human talking, like welcome to Greek heaven. So it's like this one could be the one that has category 0, means a normal message. Let me find out if that's the case. It's 0, and that's our data. We explore it, and then we need to find out that value. That's my favorite function. Value counts. Okay, I need to add another bracket. It counts. Okay. Right now we have count all the categories, right? We have 3,900 zeros and 1,800, almost 1,900 ones. We don't have the same amount for ones than the zeros. That's why it's like the prediction is not even, right? We have fewer ones inside our data set. I already have it? Cool. Then we have data info. In this case, what we do is we want to see the data type, and also we look at it to see do we have any null values. no null values, so we can proceed. We don't need to worry about that, how to fill it, do we need to delete it? Pre-processing. What we do is we use for define lambda function to do 4 steps. First, remove non-alphabets. Second, we get a token of alphabet-only list. And then we do a lambda function to run each line of value. What do we do last time is to do the assign a lemmatizer to a lambda function. So very easy introduction of the lambda function. Lambda means it works on each value. So on each message over here, we apply the lambda function, right? X means the import. You can name it whatever it is, but it should be consistent with the output. So you get a list, you get a string, and the output is a string that replaces everything that's not alphabet into a space. And the same thing is we get an X, whatever it is, we will be assigned to X, and we will get a tokenized version of X. So usually you can see this, we get a W, and for each part, each string of W, which I assume is a list, we do a stemmer to get a stemmed version of it. So that's everything. We go through it. Since this doesn't do anything to the data, it just defines the function and run really quick. And the second one would take a longer time. And we know from last time that tokenization take a lot of time, and stemming take a lot of time too. Remove non-alphabets, not that much. So it went through the first one and ran out the second one. During its running, when it's running, let's go through the second one. We split the train test dataset. This is similar to the one we did for data mining. We have train X, test X. This is Y train. This is a Y test. So we name it differently simply because this is a huge text. What we do is we split message into train and test. We split category into train labels and test labels. And what we do here is like we randomly cut it into 30% and 70%. So the text size will be 0.3. If I run it, I need to wait for the one that's running over here. We can keep going. I think it's going to the last step. So construct features for machine learning. It runs through it. Okay, good. We have bag of words. Bag of words is counting each word to get a document term matrix. And what's really happened is that you look at the feature, right? We have a list of features, but the first feature is, we'll print them out. The first feature is this. We count how much it happens over here, how much it show up in the test, in a single test. So this is bag of words. You see it over here. It uses bag of words vectorizer to do the function. You see, we define function first, and then we transform the train feature and text feature. Let's keep going. This TF-IDF. We'll get definitely a term frequency and inverse document frequency from this one. Definitely want you to look at it to just show you that everything becomes feature in a way that it's only number. Just only number. Oh, I cannot print this out directly. I need to print it. Print the first one. And this is I assume this one is term frequency, and down on right is inverse document frequency. So it become more important when terms show up less frequently, Um, and then you can see that all the words become numbers in some way that's meaningful to computer to become a feature. What you back? There are several ways to understand it. It's not only calculate existence, but also in some ways the sequence of the words are taken into consideration. We have the size window and minimum count. We use a Genism as our dictionary. So if you are really curious about what's happening, just search Genism and you will find, and also what you back. Both of them are the keyword for it. So what it do is using the part of neural network ways to give a value for this feature. Okay, it's running, and I hear my computer kind of burning in some way. Let's keep going. We have a defined evaluation function over here. What we do is we get a matrix. Every time we finish do the train and testing, we get 4 different metrics, like 4 different values inside the matrix. So accuracy, precision, recall, F1, we all record into our metrics. And it's a dictionary, as we can see over here. So don't worry if you see a big chunk of defined function in this lab, because we use it a lot. And also, when you use it, you find it very useful. You only need to know what's input, what's the output. So I will try to explain it this way so you're not confused. And over here, I'm going to talk to you about our train predictive evaluation model. We get a classifier, we get a train feature, train labels, test features, test labels. What we do is we have the classifier to fit train feature and train labels, as we can see over here. The classifier, we use that to fit train feature, train label, and we get a prediction, right? And what's the output? We get a classification report, and we print them out. And then we get the metrics, which are the 4 measures we hear about right now: accuracy, precision, recall, and F1. What else? We also get predictions. So it will return 2 measures, and it will give us a classification report, which is super convenient. I love the classification report and USUI. And this is the classification report. If you're doing today's homework, you'll see that we have precision. Positive precision is over here, negative precision over here. What you will do is you also find average precision in the bottom. And we don't, for now, our class don't require you to know the weighted average. But weighted average take consideration of the number of 0 and 1s. People also ask about question about how to calculate average F1, average precision, average recall. Do we need to do the average before the calculation? My answer is no. After you calculate the positive precision and negative precision, and you split them in half. That's how you get it. You see that? 91 is half of sum of these two, this one, positive and negative F1 score. And we keep going. We have build out backwards features. We use that on, the first one is naive Bayes, the second one decision tree, and the third one is random forest. And I have a report in the end, so don't worry if I go through too very fast. This is TF-IDF feature. We go through naive Bayes, decision tree, and random forest again. They take longer time, usually. And then we go through walk-to-back features. And we get their classification report in the end. This record is pretty good over here. That is 4 zeros and not 4 the ones. But detecting scan is good for a record as high as 0. It means that the correct or the normal mails didn't detect as a scan, right? So that's a good model if we judge it. Then we have visualized perform metrics. Don't worry about what's happening over here. What we do is over here we color the title. That's why you look at this organized and in some ways professional. You can do it in Excel in the homework, but don't worry about this if you are not comfortable with the dictionary approach. We use dictionary approach and we rename it. So, and also in a way that we do it very efficiently. But don't worry if you don't like this method, but this is the way that our TAs present to you about the result. As we can see the results, surprisingly, bag of words work really well in almost all the categories, right? Using naive Bayes decision tree, not that much, 0.1 loss miss, right? But over here, when you look at F1 scores, bag of words over here, it's naive Bayes, it worked fine, and random forest, it worked really well too. So when we look at recall, I see that TF-IDF in terms of naive Bayes and walk-to-back work, the result is poor in some way, and compared to others, definitely. And also when you look at bag of words, you see that it has higher record than others. And you see naive Bayes, it has low F1 score. I think because of they have low recall score, it brings up to the F1 score. You see that? They have a really low compared to others F1 score over here. And that's the result. If you let me to choose from all these models, or all the, like right now we have 9 combinations, right? I will first look at F1 score. And if I have the negative recall score, that would be the best, because I don't want any of my normal mails get into detect that I need to go to scan mails to look at it. So in real life, there's very specific things you should look at, but generally, I believe as F1 score could be the golden metrics you need to remember. Okay, let's keep going. I thought too much. Over here, we have an optional neural network approach that you might be interested. So keep going. We have standard neural network classification. This is a big chunk code, and we do 20 epochs, which means it runs through our data 20 times. And each time we print our result out, we get epoch, we get loss, and we also get an accuracy. And let's see how it runs. So this is BOW bag of words using neural networks. And it's running, but it didn't print out anything. So maybe in the first epoch, you see that the loss is 66. It's improving. It's improving again to 99% accuracy. A lot of time, accuracy means a lot. But it is also biased in a lot of ways that we know that our result, we have contained a lot of zeros, not a lot of ones. Many of the time, 91% is really good, but still we need to look at other measures, right? Like F1, like recall, like precision. Accuracy over here is still really good. Loss, a good measure too. I think this neural network using loss to improve their precision this time. Remember that we have Apple set as 20. So keep going, we have 20, and then we show a graph saying that we improve our model dramatically from 1 to 20 epochs. Let's keep going. We have TF-IDF metrics. We have the word to back with neural networks. As we can see that the accuracy starts from really low. It's not improving at all for the second time. What happens is that for some measure, it improves slower than others. It starts from it goes through all the measures randomly, and then it's improving and giving weights to different hidden knots, as I say. So it's improving, as you can see. It starts from Apple 6 to have 95% accuracy. '15. Almost going to end. We have really, really low loss over here. And the accuracy really good. Oh, it ran really fast for the last one. So as we can see that this one improves dramatically, right? For the second one, the TF-IDF, I think it improved the slowest compared to other two. Oh, this two look similar, but you see that the accuracy is after 20 epochs, it had 99 and 98. Not bad at all. So let's keep going. We'll look at our result. This is a way to show our result. Again, we just add neural network. As we can see, the neural network performance is not bad, and it's the best. Over here, you can see the record to 100%, and neural network compared to all others, 99%, 98%. It's performing really good. But if I choose a combination from a feature generation and also the classifiers, I believe that bag of words over here, I first look at F1, right? I think bag of words and TF-IDF neural network really work well for me. And I trust bag of words better because it runs through fewer epochs to become that good. It means that this feature is effective for this model. So if I had to choose all these models, I would choose bag of words and neural network combination. And throughout all these feature generators, we find out that bag of words, surprisingly, it's the simplest feature generator, but it has the best end result. I think one of the reasons is that it's very the way we detect scam is very straightforward. You just need to count the words that is very prominent to detect as a scam. So that's all for the lab. Thank you for watching. Hope you have a good day.